Welcome back to The Explainer. Today, we are talking about diodes. You know, those tiny little electronic parts that are, and this is no exaggeration, the gatekeepers of electricity. They might look small, but honestly, they're one of the main reasons our entire modern world even works. Okay, so here's what we've got on tap today. We're going to start with the core idea, the one-way street. Then we'll look at the standard diode and the challenges with speed and power that come with it. From there, we'll meet some diodes with very special talents, figure out how you choose the right one, and finally, peek into the future of diodes. Let's get started.
All right, section 1, the one-way street. This is where we introduce the diode. So what's the one big idea that ties this whole family of components together? Well, it's all about controlling the flow of electricity.
So take a look at these. You've got everything from these little glass beads to some pretty heavy-duty bolts. And you might be thinking, what on earth do these things have in common? Well, they're all diodes. They might look completely different, but they all share the exact same fundamental job. Think of them as the bouncers at the nightclub of electronics. They let the current flow in, but only in one direction. No exceptions.
So let's put a formal definition on that. A diode is a two-terminal component that basically forces current to go one way. It's got super low resistance in that one direction, so current flows easily. But if you try to go the other way, nope, the resistance is sky high. It's an electronic check valve, a one-way street, you get the idea. And it is an absolutely fundamental building block for pretty much all modern electronics. And you know, this whole idea of a one-way street for electricity, it's not exactly new. It goes way back to 1874, when Carl Ferdinand Braun noticed this weird thing happening in crystals. He called it unilateral conduction. Basically, electricity would only flow in one direction. That discovery was a huge deal, and it became the key to early radio detectors, like the one Jagadish Chandra Bose patented in 1901. Fast forward to 1952, and we get the first germanium power diode, which really kicked off the modern era. Okay, on to our next section, the standard diode, or as I like to call it, the original blueprint. Now that we've got the basic concept down, let's meet the most common, the OG of the diode world, the standard PN junction diode. All right, so here you can see the diode in two forms, the actual physical component on the left and its symbol that you'd see in a circuit diagram on the right. Now, that little band on the physical diode, that is absolutely critical. It marks the cathode, which is the negative end. If you put it in backwards, your circuit just won't work. Simple as that. And on the symbol, the arrow shows you the direction the current is supposed to flow, pointing right at that cathode line. This graph, the VI curve, is basically the diode's personality profile. It tells you everything about how it behaves. So look here, if you apply voltage in the wrong direction, that's the reverse bias part, nothing happens. It's off, no current flows. But the second you apply a little bit of voltage in the right direction, we call that forward bias, and for a typical silicon diode, it's about 0.7 volts, bam, the floodgates open. The diode turns on, and current can flow like crazy. It really is like a gate that needs a tiny push to swing wide open. So what's the number one job for this one-way superpower? Well, it's something called rectification. And trust me, you rely on it every single day. See, the power coming out of your wall socket is alternating current, or AC. It flips back and forth constantly. But your phone, your laptop, pretty much everything you own needs direct current, or DC, a nice, steady, one-way flow. And how do we get from one to the other? Diodes. They're the magic ingredient. They basically chop off the entire negative half of that AC wave, letting only the positive part through. It's the first and most crucial step in creating the DC power that runs our digital lives.
Okay, moving on. Section 3. Speed and power challenges. Because, let's be real, the standard diode isn't perfect. It's great, but it's not a perfect one-way valve. The moment you start dealing with really high speeds or a lot of power, you start to see its limits. And that's where things get really interesting from an engineering standpoint.
So here's the question for you. What happens when off doesn't mean instantly off? I mean, in a perfect world, a diode would switch from on to off in 0 time. But this isn't a perfect world. There's always a tiny delay. And when you're in a circuit that's switching millions or even billions of times a second, that tiny little delay suddenly becomes a massive problem. We're talking wasted energy, electrical noise, and sometimes it can even damage other parts of the circuit. And this graph right here shows you exactly what that delay looks like. It's called reverse recovery time. See, when the voltage flips, the diode doesn't just shut off. For a tiny fraction of a second, it actually lets some current leak through in the wrong direction. Why? Well, it's because a little bit of electrical charge gets trapped inside the diode when it's on, and it takes a moment to get rid of it. That little blip of reverse current you see there, that is a huge headache in high-speed circuits, causing all sorts of inefficiency and noise. Next up, diodes with special talents. Meet the specialist family. Because of these challenges, this need for more speed, better efficiency, and other unique behaviors, engineers didn't just give up. Nope, they got creative and developed a whole family of specialized diodes. Think of them as variations on that original blueprint, but each one is tweaked to be a superstar at one particular job. First up, meet the sprinter of the family, the Schottky diode. Now, a standard diode uses a junction between two types of semiconductor material. A Schottky, though, uses a metal semiconductor junction. And that's a game changer. It means there's almost none of that stored charge we were just talking about. The result? It can switch on and off almost instantly. And as a nice little bonus, it turns on with a much lower voltage, around 0.2 volts, which means it wastes way less energy as heat. It's fast and it's efficient.
Okay, now for the undisputed rock star of the diode world, the LED, or light-emitting diode. This is a diode that's been specifically designed to do something pretty magical. You pass current through it in the right direction, and it gives off light. It's that simple. And the color of that light? That all depends on the specific materials they use to build it. As you can see from the graph, different colors even need slightly different voltages to turn on. LEDs are everywhere, from the little indicator lights on your gear to those giant screens in Times Square. They've completely changed our world.
All right, prepare to get a little weird, because next we have the tunnel diode. This one operates on some pretty funky principles of quantum mechanics, and it has this one bizarre property that just messes with your head. Look at that VI curve. In that little dip in the middle, as you increase the voltage, the current actually decreases. That's called negative resistance. It's totally counterintuitive, right? It's like pushing someone on a swing and having them slow down. But that weirdness is exactly what makes it perfect for building incredibly fast oscillators for high-frequency circuits.
So what happens when you need to handle some serious high-voltage power? Well, you call in the heavy lifter, the PIN diode. Its name comes right from its structure. You've got a P-type layer and N-type layer, and sandwiched between them is a wide intrinsic layer of pure semiconductor material. That middle I layer is the whole secret. It's really wide and acts like an amazing insulator, which means the PIN diode can block incredibly high voltages without breaking a sweat. All right, next section, choosing the right diode. It really is about using the right tool for the job. So you've got this whole family of specialists, right? You've got your sprinters, your rock stars, your heavy lifters. How does an engineer actually decide which one to use? Well, it all comes down to trade-offs. As you can see from this handy chart, there's a diode for just about any application you can think of. If you're just doing some simple low-frequency power supply stuff, a standard diode is cheap and gets the job done. But if speed is what you need, like in a modern switching power supply, you have to go with a Schottky. There's really no contest. Need to emit light? LED, obviously. High voltage? PIN diode is your hero. It's always about matching the diode's special talent to the demands of the circuit.
So we're on to our last section, the future of diodes, which is all about moving beyond silicon. You might think that a component this old and fundamental is basically a solved problem, right? But you'd be wrong. The evolution of the diode is still going strong, and the constant push for more and more efficiency is sparking a revolution in the materials we use to make them. For decades, silicon has been the undisputed king of semiconductors. I mean, it's called Silicon Valley for a reason. But as we keep pushing electronics to be smaller, faster, and more powerful, we're starting to bump up against the physical limits of what good old silicon can do. So engineers are now looking at a whole new class of materials, things called wide bandgap semiconductors. We're talking about stuff like silicon carbide. And these new materials, they can handle way higher voltages and much hotter temperatures, which makes them perfect for the next generation of electronics. And just look at this graph. This shows you the difference in performance, and believe me, it is night and day. On top, you have a pretty fast silicon diode. See that big dip? That's the reverse recovery current we talked about. That's wasted energy, pure and simple, every single time it switches. Now look at the bottom line. That's the silicon carbide diode. It has, well, basically nothing, almost zero reverse recovery current. It just shuts off cleanly, instantly. That means it's way, way more efficient and produces a lot less waste heat.
So why does this matter? Well, this isn't just some numbers on a chart for engineers to get excited about. This has huge real-world consequences. Higher efficiency means less wasted energy. The ability to run at higher temperatures means you need less cooling, and when you put it all together, you can build power systems that are smaller, lighter, and can switch even faster than before. We're talking about a genuine game changer for everything from your next electric car to the massive data centers that keep the internet running.
You know, the story of the diode is just incredible when you think about it. It went from this curious observation in a crystal to a high-tech wonder material that's pushing the boundaries of what's possible. It just goes to show you that even the most basic, fundamental parts of our technology are always evolving. So as we keep demanding more and more power from smaller and smaller devices, it really makes you wonder, which fundamental component is going to be the next one to get a massive, revolutionary upgrade? What's next?